So now what we're going to talk about are geometric sequences. So previously we've looked at arithmetic sequences, and that was where we added or subtracted a certain amount between each number in the sequence. So what happens if the sequence actually has a different pattern? So let's, for example, look at the numbers. I better change my pen colour. Let's look at the numbers 2, 10, 50, and 250. Now, what is the pattern between all of these numbers in this sequence? So what you can see is the pattern here is that we're actually multiplying by 5 each time. So we start with 2, we multiply by 5, which gives us 10. We multiply by 5 again, which gives us 50, and so on through the sequence. Now, what we call this when we're multiplying to get from one number to the next in the sequence is what we call geometric sequences. Okay, and so obviously there's going to be a different equation that we use to relate all of the numbers in a geometric sequence compared to what we had seen with the arithmetic sequences previously. So if we think about this number sequence that we've got here, what are we doing exactly to the 2 to get to the 10? Or the 2, the starting number in the sequence, to get to any other number in the sequence. So let's look at the difference between the 2 and the 250. Okay, so t to the n, that's going to be our term number. Okay, so the term number in this case is term number 4. Is 250 is our term number 4. Okay, so 4 is going to be our n. That's our term number there. So what are we then having to do to the 2 to get to the 250? Okay, so if we know that 250 is our 4th term, okay, we're taking the 2, which is our initial term, so that's our T1. So T1 is equal to 2, that's the initial term in the sequence. And we're multiplying it by 5. So that's what we call the common ratio. So 5 is our common ratio, and that's what we're multiplying by each time we go through the sequence. But to get from 2 to 250, we're not just multiplying by 5 once, but we're multiplying by 5 1, 2, 3 times. Okay, 5, so we're taking 2, we're multiplying it by 5 to get to the 10, we're multiplying it by 5 again to get to our 50, and we're multiplying it by 5 again to get to our 250. So what we've done is we've taken T1, okay, and we've multiplied it by 5 3 times. Remember, 5 times 5 times 5 can also be represented as 5 to the power of 3. Now, what do we notice here? 250 is our 4th term, okay? And what we're doing to find our 4th term is we're taking the common multiplier, a common ratio, which is our 5, and we're raising it to a power of our term number, take away 1. So that's our 3. Okay, so to summarise with this equation up the top here, this summarises what we've just looked at. The term number, t to the n, that's our term number. Okay, so that's if we're wanting to find any term in this sequence. N is the number of the term, okay? Any term is going to be equal to the initial term, T1, multiplied by R. Now, R is what we call the common ratio. So you can think of that as what you're multiplying between, what you're multiplying each number by to go up to the next number in the sequence. So in this case, it's 5. And we're going to raise that common ratio to a power of n take 1. So the term number, take away 1. And that's the equation that's relating our geometric sequences to each other. Okay, so let's look at an example here. If we consider a sequence like the following: 5, 15, 45, and 135. Okay. First, we might say, prove that this is a geometric sequence. Okay, and for this to be a geometric sequence, we have to have each number being related to each other by some sort of multiplication of a common term or a common ratio. So if we do 5 multiplied by 3 is equal to 15, 15 then multiplied by 3 is equal to the next number in the sequence, which is 45, and we multiply 45 by 3, which is going to give us 135. So therefore, because we have a common ratio, this is a geometric sequence. Okay, so if we're now to write the relationship between this sequence, okay, how are we going to describe this sequence? So any term number in the sequence is going to be equal to the initial term number. In this case, it's 5, okay, multiplied by r, which is the common ratio. The common ratio in this case is 3, raised to the power of n take 1, okay, raised to the power of n take 1. So n is the term number minus 1. So this is going to be the equation that is used to describe this geometric sequence here. Now the final thing that I'm going to look at is how we would find a term number in this geometric sequence. So if we're asked to find, let's look at the 10th term number. So if we want to find term number 10, that's going to be equal to 5 multiplied by 3 to the power of n take 1. Now our n in this case is 10, okay? So 10 take 1 is 9. So our term number 10 is going to be equal to 5 times 3 to the power of 9. So if I quickly do that, 3 to the power of 9 multiplied by 5 is going to be equal to 98,415. So that's going to be the 10th term in this sequence, geometric sequence here. So what we can also look at now is the relationship between compound interest and a geometric sequence. And if we look at the equation that we use for compound interest, it's actually the same equation that we use for our geometric sequences, because compound interest is calculated each year or each interest term, okay? And at the end of that interest term, the new interest for the next term is calculated based on that final amount. So looking at an example, if we, for example, started off with, we started off with $100 in a bank account, okay? If we knew that that was going to increase, the interest rate was 10% per year, and it was compounded at the end of each year. By the end of the first year, we would have $100 plus the 10% of 100, which is another 10. So we would have $110. Now, if we look at the relationship between 100 and 110, the difference between these is we're multiplying it by 1.1. Okay, so we're multiplying our 100 by 1.1, which gives us our 110. So that's going to be, the 1.1 is our common ratio. That's the same as our common ratio. That's the difference between the initial value and what you'll have at the end of each year. So similarly as what we saw for geometric sequences, we can also use the same equation that we use for geometric sequences to relate to our compound interest. Okay, so what we can say is that Again, using the same symbols, T1 is going to be the initial amount of money, and then we're going to have R, which is our multiplier in this case, what we call a multiplier. This is the same as our common ratio that we saw previously. Okay, so it's the same thing. It's the percentage or the amount that each number in the sequence is increasing by each time. Okay, so let's just move that up. Next we have, that's going to be our term number again, or the amount after n years. Okay, and again we can use the same equation here. Okay, so Tn, the amount that we have after n years, is going to be equal to the initial amount, okay, multiplied by the common ratio or the multiplier raised to the power of n take away 1. Okay, so we can use this to work out compound interest as well.